Hi, this is lecture 12 of IISER. So, in last session we have seen, we ended the last session with the following observation. What is it? Suppose we have two functions, f from u to r and g from v to r, such that f of u is subset of v, then these data along with this condition gives a map G compose f map from u to r. Then I have said, if these two are continuous functions, this implies this is a continuous function. Then I said, we are trying to prove this using sequence criteria. It takes some time, and so that's why we need a we need an alternative description of continuous functions. All I am hoping now is you have tried proving that this is continuous using sequence version, and you have realized it is easy. It is not difficult. I was just bluffing. It is very straightforward, even for this case also, that if these are continuous functions, then this is a continuous function. So I can just hope that you have really tried that using sequence version, and it's straightforward. Continuity of these two functions implies continuity of this function. That also, so then what is the reason, why do we need a alternative description? If I give some explanation, it will not be very clear. I will give the definition, then maybe when we go further we will realize where are we using that description. So the description is the following. Okay, so let us take a function f from u to r, and let us take an element a belongs to u. So we already know what does it mean to say function, this function being continuous at this point a. What is the definition? For every sequence in u that converges to a, the image of the sequence is also converges to f of a. That is the description using sequence version. Let us now introduce the continuity of f at a using epsilon delta definition. What is it? So it says the following: given epsilon positive, there exists a delta positive such that some condition is satisfied. What is it? If an element y being an element of u satisfy the condition that y belongs to this interval, then this implies f of y is an element of f of a minus epsilon f of a plus epsilon. This is the description, very simple. A function f is said to be continuous at an element a belongs to u if the following condition is satisfied. What is it? Given epsilon, there exists a delta such that for every y in u, with the condition that y should be between a minus delta and a plus delta, then f of y will be in between f of a minus epsilon, f of a plus epsilon. This is the notion of continuity using the so called epsilon delta description. So let us first see whether this description is equivalent to the sequence version. So let us take a function f from u to r. Let us assume that this function f is continuous using the epsilon delta description. Then let us prove that it is continuous with respect to sequence version. So assume f is continuous as per epsilon delta definition. So I have not mentioned here, if f is continuous at every a belongs to u, then we say this function is continuous function. Here we are defining point wise initially, then we are saying this function is continuous as a whole if it is continuous at each point a belongs to u. Now let us come back to this. So now what we are doing, we are trying to realize whether those two notions are actually same, the epsilon delta definition and the sequence version, are they really same? Yeah, that's what we are trying to see. So we are starting with the function f from u to r, and we are starting with the assumption that it is continuous as per the epsilon delta description. Then we are trying to prove it that the sequence assertion is also correct. So let us take a sequence xn converges to A. A is an element of u, that is what we are starting with. A belongs to u. Then we have taken a sequence in A. Then we have taken a sequence xn in u that converges to A. Then we are supposed to prove that f of xn converges to f of A. This is what you are supposed to prove. So trying to make use of this epsilon delta description, we will try to prove that this is the convergence sequence. So what should be our strategy? Starting with an epsilon positive, we need to find an element n belongs to n such that for every n greater than n, f of xn belongs to f of a minus epsilon, f of a plus epsilon. This is what you are supposed to prove. What we have is just this, that this sequence xn converges to A. What do you know about sequence convergence? Given epsilon positive, there exists n belongs to n, not the same n, some other n belongs to n such that the following condition is satisfied. Xn belongs to A minus epsilon and A plus epsilon for all, say n tilde, whatever it is. Xn converges to A means this: given epsilon positive, there exists a n such that for every n greater than or equal to n, this is the condition. But the epsilon delta description of continuity says, given epsilon, there exists delta such that whenever xn belongs to A minus delta, A plus delta, right? There is we have written epsilon here, but only if it is only if this is delta, we can apply the notion of continuity and conclude that this is true. But we have here epsilon, not delta. So what do we do? Let us go back and see what is the mistake that we have made. Given epsilon positive, we are trying to make use of this notion of convergence of the sequence xn to A. So we applied epsilon for this, then we got n belongs to n with this condition being satisfied. But this is not very useful now, because the continuity of f using the epsilon delta definition says that element xn or y, whatever it is, it should be between A minus epsilon, A minus delta and A plus delta. But here we got something else. So what do we do? Instead of applying for epsilon positive, let us apply for delta. See, we have fixed an element A belongs to u. So once I fix epsilon, delta is fixed. Apply this convergence idea for delta instead of epsilon. Given epsilon, there exists a delta. For this delta, I make use of this description of convergence. So for delta positive, there exists a n such that for every n greater than or equal to n, xn belongs to A minus delta and A plus delta. So let me erase this. Now we can directly apply the definition of continuity. This implies this that we have already seen just now. So the mistake that we have made before is the following: we have applied this notion of convergence for epsilon. That's why we got epsilon here, and which is not useful at all. What we need to do is, we should apply the delta that we got. Given A and epsilon positive, there exists delta. So let us apply this delta for this sequence, and then we are done. Xn belongs to this interval implies fxn belongs to this interval. That is just because of this whatever I have written here. So these are the small tricks that you need to be careful. Depending on what you want, see, we want here we want here a minus delta and a plus delta. Initially we have written epsilon here, which was not useful. So depending on the necessity, we have to change the starting point. This is very simple. Yeah, this is very simple, nothing to explain about that. We want here delta. If I use epsilon, I get epsilon. If I want delta, I should use delta. Do I have delta? Yes. Given epsilon, there is delta already. This is after fixing a, that is that we have already fixed before. So what does this say? This says epsilon delta description implies sequence version. Now let us try the other way. Suppose we know that a function f satisfies continuity condition in this version. Sequence version it satisfies. Let us try to use this idea. So let us try to use that it is sequence continuity and prove that it is continuous using epsilon delta description. So what do we do for that? Starting with epsilon positive, we should look for a delta positive such that, see all these I am fixing a. After fixing a only, we are proceeding further. So given epsilon positive, we should find a delta positive such that whenever y belongs to a minus delta and a plus delta, we should have f of y belongs to f of a minus epsilon, f of a plus epsilon. This is what we need to prove. This implies this. So now you can pause the video. And try by yourself that given epsilon, can I find a delta positive such that this is the case. So after struggling for some time, you will realize that it is not very clear how to produce delta from epsilon. So maybe we come to the conclusion that this is actually wrong, because we try sometimes, then we don't know what to do, so we realize that we conclude that this is actually wrong. That sequence version does not imply epsilon delta description. So what does this mean? This means for some epsilon positive, we are not able to find a delta with this condition, right? If this condition, whatever I have written here, if this condition is false, what does it mean? There exists epsilon positive such that this condition, whatever I have written here, does not hold. You see, this is wrong. That's what it means, right? So this is wrong. What does it mean? It means for every delta, I can find some y here, but this is wrong. I mean, you should get used to this kind of understanding. I mean, this statement involves many parts. I am saying this statement wrong means what? You should go back and see how did you define this statement. For epsilon positive, something happens. If this whole thing is wrong, what does it mean? There exists epsilon positive such that this does not hold. So we will write that first. There exists epsilon positive such that this condition does not hold. Now this also is involved. This also involves many parts. So let us understand how do you write this. At least till here it should be clear. Now let us try to write down this. So this is wrong means what? There exists delta positive such that something is happening. The opposite of this is what? For every delta, this is not happening. So let me write down that. So there exists epsilon positive such that for every delta positive, this is not happening. So what was this? This says again, for every y belongs to this is true. If this condition is false, what does it mean? Again, whatever I have written here, we have to just copy paste the same thing here. For every epsilon positive, something is happening, the opposite of that is they register epsilon positive such that something is not happening. So for every y something is happening, opposite of that is there exists a y such that this is not happening. So these two are clear. This part is the following: there exists a y belongs to a minus delta and a plus delta such that this is not happening. F of y not an element of f of a minus epsilon, f of a plus epsilon. Let me say one more time. We are assuming that this statement is wrong. So maybe I will add something before. So given epsilon positive, there exists delta positive such that, so for all y belongs to this interval, we have f of y in this interval. As I said, suppose this is wrong, we should start at the first description and then we started here, then we proceed further. So this is wrong, which means what? Whatever was correct for every epsilon, the wrong statement associated to that is there exists epsilon positive such that something is not happening. That's what I have written here. There exists epsilon positive such that something is not happening. This is the case. Now again, so this is not happening. How do we write down that the corresponding statement? There exists delta such that for every y this is true. What is opposite of that? For every delta this is not happening. That's what I have written here. For every delta positive something is not happening. Again I have to come to this situation. The correct statement is for every y belongs to this interval we have this condition. What is opposite of that? There exists a y belongs to this interval such that this does not happen. That's what I have written here. There exists a y belongs to this such that f of y is not an element of this. It is actually easy. It just takes some time, 5 minutes. It takes some time to just read it again and again. You will be able to understand. It's not a difficult part. Now what? So we got this. So even if we assume sequence criteria, we have realized that this may not be correct. So we have written the corresponding statement. What is the corresponding statement for this being not true? There exists epsilon positive such that for every delta positive there exists a y belongs to this interval such that f of y is not an element of this interval. So what do we do after this? So we started with the assumption that it satisfies this condition, right? Sequence version. So we should make use of that sequence version, which means what? We should get a sequence first. So we are looking for a sequence. We are talking about convergence, we are talking about continuity at a point A. So we want a sequence that converges to A. This is what we want. Do we have that, something like that? Again, the trick I am going to say no, we will repeat again and again multiple times. So observe this situation. For every delta positive there exists a y inside this. Now what? We are looking for a sequence inside U that converges to A. Okay, so we should somehow make use of this description. So sequence is a set indexed by natural number. So for each natural number we need an element inside U. If you observe, one can get some element with this description. For every n belongs to n, for every n belongs to n, 1 by n is the positive element. So we apply this for this element 1 by n and get an element yn in this interval. So for n belongs to n, we have 1 by n positive for that element what does this say? There is an element y belongs to here, because we are indexing by natural numbers, we will be writing delta by 1 by n, where we will be replacing delta by 1 by n and y by yn or xn, whatever it is. So, the register xn belongs to a minus 1 by n and a plus 1 by n, but f of xn is not an element of f of a minus epsilon, f of a plus epsilon. So, let us first see what does this say. Let me write down this. That says a minus 1 by n less than xn less than a plus 1 by n. That is what it says, right? xn is element of this interval, which is simply this. Observe that this, if I take the corresponding sequence a minus 1 by n, this converges to a. Similarly, this converges to a. By squeezing theorem, this sequence should converge to a. So, what do we have? We get a sequence xn that converges to a. Even in that case, this condition says, see, this is true for every n belongs to n. This says this sequence f of xn does not converge to f of a, because see, what do we want? If I want f xn to converge to f of a, we want to get some element n belongs to n such that for every n greater than or equal to n, we want this condition. We want this to be element of this, but what do we have? We have this. For every n belongs to n, for every n belongs to n, this is the condition. So, that says f xn does not converge to f of a for this epsilon. So, even though xn converges to a, we have f of xn does not converge to f of a. So, this is a contradiction to the assumption that the function f that we are starting with is a continuous function with respect to sequence function. So, whatever we have assumed about this condition, it is not true. What we assumed that this is not happening. So, so because the assumption is wrong, it turns out that this is actually true. Given epsilon positive, there exists delta such that for every y belongs to this interval, f of y is in this interval. So, this says epsilon delta is equivalent to sequence convergence. When we are talking about continuity, these two notions are actually same. Okay. So, now we got a correspondence between these two notions of continuity at a point a or on the whole domain of the function. Okay. Now, let us try to understand about the behavior of the function, assuming it is continuous at some point. So, let us take a function f u to r continuous at an element a belongs to. So, first question that we want to ask ourselves is the following. See, if a belongs to u, so f of a is an element of r. So, inside r there are three possibilities, either this is equal to 0 or positive or negative. The question is following: if I take a continuous function, if I take a function continuous at a and suppose it is positive, what can I say about the behavior of the function around a neighborhood of a? Similarly, if f of a is negative, what can I say about the behavior of the function f around a neighborhood of a? Okay. So, let us assume that f of a is positive. Then we have to conclude something from here. That is what we are trying to see. So what do we do from here? Just now we have seen the definition of epsilon delta definition of continuity of a function f at an element a. So, it starts with a suppose somebody gives epsilon positive, there is a delta, something happens. Here f of a is positive, so one can actually take epsilon to be f of a. We will see what happens. Epsilon is equal to f of a, positive element. So, there exists a delta positive such that for y belongs to a minus delta and a plus delta, we have f of y belongs to f of a minus epsilon and f of a plus epsilon. As epsilon is equal to f of a, this difference is actually 0. F of a minus epsilon is actually 0. So, we will remove this part and simply put 0. Fy is in this interval. What does it mean? 0 less than f of y. So, for every y inside this interval, we have f of y positive. So, if I started with an element a belongs to u such that f of a is positive, then there is interval around a, in the whole interval, this is the situation. The order remains. If it is positive, this is positive. If it is negative, do you know anything about this? We can do the same thing. If this is negative, if f of a is less than 0, but if you want to apply the epsilon delta definition, we want epsilon to be positive. So, what do? We simply put minus f of a for epsilon. Then this will be same f of a minus epsilon, but this part will be equal to 0. Epsilon is equal to minus f of a plus epsilon will be 0. So, we will remove this and simply put 0. So, what does this say? F of y is less than 0. So, the idea is clear at least. If f is continuous at u, if f is continuous at an element a, if I know f of a is negative, I can find a neighborhood around a in which f is negative. For this function f at a point a belongs to u, if an f of a is positive, then as we have seen before, there is a neighborhood around a on which f is still positive. That is what you have seen before. So, this is the first observation around regarding a function that is continuous at a point a when with respect to the being positive or negative. Okay. So, let us now ask a different question. Suppose, see what we have seen just now is the following: for a function u to r, if for an element a belongs to u, if f of a is positive, there is a neighborhood on which f is taking positive value. If f of a is negative, then there is a neighborhood around a on which f is taking negative values. Let us ask the following question. Let us assume there are two elements in u, not just one, two elements in u, a in u, b in u, such that f of a is negative, f of b is positive. What can we say about this? You do not have to say anything about this immediately. Let us see what did this give. So, let me write down the line. Let us assume that a is less than b. I mean, one of these should be true, either a less than b or b less than a. Otherwise, if a is equal to b, this cannot happen unless f of a is equal to f of b is equal to 0. So, I am assuming that a is less than b. Now, this condition says the following: there exists a delta a minus delta a plus delta such that f restricted to this interval is negative. For every y here, f of y is negative. Again, f of b is positive. So, there exists a delta such that b minus delta and b plus delta in this interval f of b is positive. If you observe, see these two are I have written this, they are same. So, let us write down this as delta 1 for a, delta 2 for b, just to differentiate those two. There is no reason why they are same, right. So, the idea is just this: in this interval f of y is negative, in this interval f of y is positive. That is what you have till now. Now suppose, just for suppose that see I am writing these two in this position, that these are actually disjoint sets. It is possible that there is some intersection, right? One can ask that this element to move to the left side, you can just request them politely. See, I know for sure that in this interval this is the case. There may be a bigger interval in which this is true. How do we know that it is not true? So we can ask this element to see, go back to the left side, check if this is still satisfied even if you go to the left side. So you tell that to this person and ask whether this condition is still satisfied. Similarly, you can ask the same thing for this person. Ask this a plus delta 1 to go to the right hand side and see if even if I go somewhere here or here or here, this condition is still preserved or not. So in a very nice situation, what happens is the following that these two actually intersect, in the sense a minus delta 1, a plus delta 1 intersection b minus delta 2 and b plus delta 2 is non-empty. That says I have an element, some element y belongs to these two sets. This set is this set is this. Now y belongs to this set, which means what? F of y is negative. Similarly, y belongs to this set, which means what? Which means y belongs to this set. This means f of y is positive. What does these two conditions says? So in a very nice situation, it is possible that these two deltas go to the corresponding left hand, right hand side. They just move some slight, they just take some slight step and make sure that these two are actually intersecting. Then we have an element y belongs to u such that f of y is 0. This is what is called intermittent value theorem. So what does this say? Now we have moved this to the right side, to the left side. So let me so this new one is a plus delta 1, this new one is a b minus delta 2. It is this. So here, if I take any element in this intersection, f of y is 0. So what does this say? If I take an element a belongs to u, b belongs to u with a less than b, such that f of a is negative, f of b is positive, there exists a y belongs to a comma b such that f of y is 0. This is what is called intermittent value theorem, as I have written here. No, this is only an idea. I am only saying it is possible that this is the case. How did we come to the conclusion? That we have seen that for this a, because it is f of a is negative, there is some interval on which f takes negative values. B, which is greater than a, is such that f of b is positive. So there is some interval on which f takes positive values. There are two intervals. One possibility is they intersect. They can intersect. There is no problem with that. If they intersect, what do we get is the following. In the point of intersection, f of a satisfy this property and this property, which means f of I is 0. That is what I called as intermittent value theorem. Now see, that is only, so all we have done is we have requested this person to move to the right hand side, this to the left hand side. but that is not a proof. So we need to give a proof. So this is only some idea that if we ask somebody politely, they might help us to reach where we want to reach. So now that is only some idea. Let us try to write down the proof. Actually, whatever I said, it involves it also has a proof, a part of the proof. What I am asking is the following. I know before that for this A in this interval, f of that f restricted to this interval is negative. All I am asking is, I will just move to the right side slightly and still see whether this is satisfied or not. Right? If I can move it much further, I cannot reach B, because for B, f of B is positive. So this condition is not satisfied. So what we ask is, till what position can I move to the right side of this such that this property is still satisfied. So let us write down that what we are saying is the following. I am simply asking elements of AB such that f of y is still negative. This is what I am asking. Elements of AB such that f of y, so f of y is still negative. This is what we want to, okay, this is what we want to study. We want to see whether how far we can reach. This does not have B, that is for sure. B is not element of V, that is for sure, because f of B is positive and it is not 0, f of B is not equal to 0. So B is not element of E, and what can I see is that E is bounded below by A, bounded above by B. Right? Just now I said that if you can observe that whatever I am writing, that E, it is subset of this. B is not there, B is excluded. So this element B is an upper bound for E. Now what do we do? Whenever we talk about a set with an upper bound, the first thing that we should come to your mind is supremum. So let C is equal to supremum of E. Okay, C is equal to supremum of E. Now what do I do? I am trying to apply the notion of continuity of the function f at points A and B on the whole U. There are two ways. One way is use epsilon delta definition, which we have already used here. Right? That is how you got this these intervals, right? The way we got this interval is by using epsilon delta definition. There is one more equivalent definition. What is it? Sequence version. If I take a sequence in U, converges to some element A, x converges to A inside U, then the image of the sequence converges to the corresponding element f of A. So let us see if I can use, let us see if I can produce some sequence inside U. See, one thing that I have not said when we are talking about sequences is the following. I did not say that precisely because it was not relevant at that place. Now it is relevant. If I take a subset of R, if I know it is bounded above and L is supremum of E, then I can get a sequence inside E that converges to L. This I have not said before because there is no way that I can use that at any place. Now is the time, so now I am saying that result. For any bounded above subset of R, if L is the supremum of E, I can find a sequence inside E that converges to L. How do I see that? The only property of supremum I know is the following. If I take any element less than this, then this is not a upper bound of the set E. So if I take some element epsilon positive and L minus epsilon is less than epsilon. This is not an upper bound of this. What does this mean? This means there exists a x epsilon belongs to E such that, see, we are saying that this is not an upper bound for this. So, there exists x epsilon such that L minus epsilon is less than x epsilon. See, but we are looking for a sequence. So, we want see, we got some element in E, but if we are looking for a sequence in E, we want a set indexed by natural numbers. So, instead of looking for arbitrary epsilon positive, let us take the following epsilon positive. Let us take 1 by n. For this 1 by n, there exists a x n here. Instead of epsilon, I am writing as n here about the index such that epsilon is replaced by 1 by n, x epsilon is replaced by x n. So, L minus 1 by n is less than x n. This is true for every n belongs to n. So, what do we get here? We got a sequence in E, right? This is what we have for every n. We got an element in E, n goes to x n. This is a sequence satisfying this condition. Now, the question is, see, we are looking for a sequence that converges to somewhere. We got only this much. So, what is this? L minus 1 by n is less than x n for every n belongs to n. This is what we have. Now observe the following, that this element L is supremum of E, which means it is an upper bound at least. X n being an element of E should be satisfying this condition. This should be true because L is an upper bound of E and x n is element of E. So, this is true, x n is less than L for every n belongs to n. Now what? Again the same squeezing theorem. This sequence, if I take the corresponding sequence, this sequence converges to L. This is a constant sequence. This converges to L, which implies that this sequence converges to L. So, what do we get? We got a sequence x n in E such that x n converges to L. Fine. So, okay, we got diverted slightly. Let us go back to the place where we got diverted. We got some element, we got an element C that is supremum of E. Then this is the diversion. Using this idea, using this result, what we get is the following. We got x n belongs to E such that x n converges to the supremum that we are writing as C. Right, C is the supremum that we are mentioning. This C is actually less than B. This C actually less than B. What we have is, for every element in E, this is less than B, and so this is what we have. Let me write down this clearly. So, C is less than B. So, F is defined on C also. So, this sequence, whatever you have, one can apply convergence, one can apply the continuity description for this sequence and get the following: f of x n converges to f of C. Now, because x n is an element of E, f of x n is negative. So, what do we have? We have a sequence that converges to f c such that each of these elements is negative. What can you say about the corresponding limit? This also I have not said in the when we are talking about sequences, because there it was not relevant. So, now we got a reason to think about it. Let us think about it now. So, what is it? Again a digression. So, we got a sequence a n such that a n is say positive for every n belongs to n and an converges to a. Then we are asking, can I say anything about this being positive or negative? Something we should say. Suppose A is negative, then see whatever the trick that I applied here, for epsilon I took minus epsilon, right? Where did I write that? Yeah, here. F of A was positive when we are trying to make use of this continuity version of epsilon delta definition. We took epsilon to be f of A if it is positive or minus A if it is negative. We do the same thing here. If A is negative, one can take epsilon to be minus A. For this positive element, there exists a n belongs to n such that an minus A is less than epsilon. This is same thing as saying minus epsilon less than an minus A less than epsilon. Okay, now see epsilon was minus A, so I can just replace this by minus A, right. So if I focus only here, an minus A is less than minus A. So these two gets cancelled and we got an to be less than 0. Right? What does this say? Just this part. This implies an is negative, but we assumed that an is positive for every n belongs to n. So this assumption is wrong. If this is wrong, what is correct? The correct thing is A should be greater than or equal to 0. Again, suppose we assume that an is a sequence such that an is negative for every n belongs to n and an converges to A, then the same this idea implies that the corresponding limit A is less than or equal to 0. So depending on this limit is fixed. Now how do I use this? Again we'll go back to the place where we got diverted. So fxn is a negative for every n belongs to n. Xn is an element of E, so f of xn is an element. If f of xn is negative, that's how E is described, right? For every y belongs to this, f of y is negative. So for this xn being element of E, f of xn is negative. We have just now seen that fxn converges to f of c. So f of c should be less than or equal to 0. 0 is a possibility. So what do we have? F of c is less than or equal to 0. We are trying to prove that f of c is 0. That is what intermediate value theorem says, right? There is some c between a and b such that f of c is 0. So we got one part. We need to get the other part. What do you think we should do? We should try to prove that f of c is greater than or equal to 0. Just now we have seen that suppose we have a sequence converging to C, we applied the corresponding f, the continuity description of f, and then proved that is f of xn, xn is element of E, f of xn is negative, so the corresponding limit which is f of x is less than or equal to 0. Suppose we get a sequence, say yn is a sequence inside U such that f of yn is positive for every n belongs to n and yn converges to C. Yn is a sequence in U such that yn converges to C, then one can apply the same idea and conclude that f of c is positive greater than or equal to 0. Now how do I get a sequence in U that converges to C? So what was the diagram? This is A, this is B, this is somewhere around C. Now and this whole part, this is E. I am looking for elements in U. U will say something around this. this whole thing is U, let us assume. So I need to get some element yn inside U such that yn converges to C, and this should be the condition. Suppose I take yn here, then f of yn is negative. So I should take a sequence outside this part, either here, or here. Now given any point in R, one obvious way to get a sequence that converges to that is the following. You fix any element P belongs to R. There are two sequences that converge to P. What is it? From the left side and from the right side. P plus 1 by n converges to P, 1 by n converges to 0. So P plus 1 by n converges to P. Similarly, P minus 1 by n converges to P. This is convergence, no, not this symbol, convergence to P. So here we do the same trick. If we take some elements here, come from the right side, so we should be C plus 1 by n converges to C, that is for sure. But the only problem is the following, that this may not be actually contained in B, right? If suppose it is very close, that it may not have all these elements. So how do we fix this? This is one more trick that you need to understand. So see, this is a fair sequence. This converges to C, that is fine. The only problem is that this element is not inside this. So what is the problem? So C less than C plus 1 by n less than B. So we want this to be the case. For this to be the situation, what we want is following, that C plus NC plus 1 is less than NB, right? This is something as this, right? So this implies what? NC less than NB minus 1. All I know is that C is less than B. Maybe after a certain stage this may not hold. So I don't really have this case always. Okay. Now what we are doing is we are trying to change this sequence slightly so that convergence remains same, but this whole part is in between C and B. That is the idea. So what we do is we will try to see if I make any change here, there is no guarantee that I reach C. We will make change here, so that so we will make some change here, so that the corresponding sum is still inside C. The change we are proposing is the following. Instead of 1, we take B minus C. B minus C is positive. So this element is still right side of C. So this element is not here. So f of this will be still positive. So this is sequence that comes to C, that is fine. But is it in between C and B? For that, what we want is this. We want B minus C to satisfy this condition. Do we have this? NC plus B minus C is less than NB. Do we have this condition? We will just ask this B to go this side, and let me erase this. So we are asking this B to go here. So we have NC minus C less than NB minus B, and this is always true. But because C is less than B, or if you want to write one more step, I will write one more step also. So n minus 1 times C less than n 1 times B. C is less than B. This is a natural number. So if I multiply by any natural number, the order does not change. So because C is less than B, this holds. So this sequence is the correct sequence that is useful for us now. 1 by n was not useful. 1 by n was obvious sequence that we should consider, but that sequence has a problem, that it may not be contained in this part. So for that we have changed the sequence slightly, and then we got this sequence, C plus this converge to C. As I said that this is outside E. E was the whole elements for which f of the f of that elements is negative. This is not inside C, so this is positive. So f of this converge to f of this is positive. So this the limit is so this says f of C is greater than or equal to 0. So we got previously f of C less than or equal to 0. Now we got f of C greater than or equal to 0. So these two combine and say that f of C is 0. So this is the so called intermediate value theorem. It took some time, but it is not difficult. It is just that I have not done two results of sequences previously, because that was not useful at that time. Now it is useful, so I have to do it now. So only when the necessity comes, we will see some theorems regarding sequences or functions or anything. So that's all about this session. In the next session we will see some other results about continuous functions.